Hello, everyone. Welcome to the third day of our ALF workshop. Today we started a bit earlier, and we start today with two contributed talks. The first one will be by Maxim Trushin from the National University of Singapore. He's going to talk about the flat band specific highly conductive electron correlated state. The stage is yours.
All right. Okay, welcome for the third day. And so I will talk about very long project which we have finally completed a few weeks back with publication in Physical Review with editorial suggestion. So I hope you will like this work as editors from Phys do. Okay, just a little bit about the place I'm come from. So because many people, especially from the United States, for some reason mix up Singapore and Hong Kong. It's completely two different places. So Singapore is on the equator, and it's a small independent country. So if you go there, so you probably will see this. Oops, sorry, what I did.
Just hide this here because no, sorry. No.
Yeah, so you probably see this skyline, but if you go a little bit westwards, you will find this much more modest building with our institute, where I have a position now. All right, so even though Singapore is quite away from Würzburg, so our wave functions are somehow very like a little bit overlap. So therefore, you sometimes find people from Singapore here in Würzburg and people from Würzburg in Singapore. So they have like a kind of tunneling from time to time. So I have to admit from the beginning that I'm not a quantum Monte Carlo guy. So even though I have maybe one or two publications with another Maxim who is sitting here, so who was doing the quantum Monte Carlo in our collaborative work, so I know very little knowledge about quantum Monte Carlo. So I'm actually doing mean field. And I hope that so there are some overlaps between these two fields where we can collaborate. Okay, just a very brief introduction. What is mean field, right? So if you have a many-body system with interactions between electrons, let's say, the interaction Hamiltonian is very complicated. It's quartic in terms of the C dagger C, right? And what mean field does is, so you make some assumption. And you reduce the Hamiltonian to the quadratic in C dagger C. And all interactions are in some kind of average field, which is called mean field, so that the electrons behave as if they're independent particles, but in some complicated average field, which includes all the interactions. But the problem is that you simplify drastically in such a way that it doesn't guarantee you that the results are correct. Therefore, if you open like many textbooks on mean field theory, like Bruce and Flensburg, the chapter which describes all this mean field theory is usually, so it has a title like the art of mean field theory. So it's not like a well-defined recipe which you can use, right? So you have no guarantee. But there are very famous examples like BCS, right, which is very simple BCS mean field theory, but still it gives you physical answers on a very it's very famous for this. Okay, so therefore what I will tell you later, please take it with some kind of grain of salt, it may not be completely true. Okay, this is my toy model. You have two bands. One band is completely empty, one is occupied, and they're touching in one single point. And so this is my toy model to study interactions. So the main point here is that the bands can be adjusted in such a way that the density of states at the touching point can be different. So to do that, I assume the dispersion. So it is in k in the power of p. So if p is equal to 2, then we have a simple parabolic bands. And the density of states is the same no matter where you're at energy. Even at the band intersection, it's still the same as at any other energy. But if P is much larger than 2, the density of states is drastically increasing at a band intersection. So therefore, we expect that we could have some amplifications, amplification of the interaction effects at the band intersection. Yeah. So the advantage of this model is that we can adjust P, so the power of dispersion, and in such a way we also can adjust the interaction effects continuously from P equal to 2 to P, let's say, infinity when it's completely flat. Okay, now we do mean field approximation. So what you see now on the screen is just conventional BCS-like pairing approximation. So that means we have a pairing between two electrons with opposite momentum, opposite spin index, and having the same energy. So so here in notation, the sign in front of K is actually the band index. Plus is for upper band and minus for low band, and the bar means negative K. So of course you have interaction, so therefore you can scatter from K to K prime. But the main point is that the pair is still made of two electrons having the same energy, opposite spin and opposite momentum. And the result is known as a BCS superconducting state. But now we do something similar, but not completely the same. So we make pairing like this. So what we call crossband electron pairing. So we still pair electrons with opposite spin, opposite momentum, but energy is also opposite if you count from the band touching point. So you can say, of course, you break time reversal symmetry, but no, I don't, because I have added another Hamiltonian on the right, which so and if you sum up these two, then the total Hamiltonian is time reversal invariant. So so on the left you pair spin down electrons from the lower band with spin up electrons in the upper band, and on the right you do the same, but with spin up electrons from the lower band and spin down electrons from the upper band. So time reversal invariance is okay.
Is this still one band, or do you have multiple bands?
So two bands, just two bands. Yeah. So there is no lattice here, so I don't consider values and all this additional flavors of electrons. Yeah, so it's still yeah. So okay, so then I can give you already the answer. So if you do this pairing, if you do this mean field assumption and do the same way as Bardeen Cooper Schrieffer did like 60 years ago, you arrive at the following state. In the normal state, what you have is Fermi C in the lower band, which is just a normal Fermi C, and in the upper band you have vacuum. And once you switch on this kind of interaction, I told you in the previous slide. So the state is separated into three sections. So similar to the BCS, you have an order parameter which is delta, but this delta is not a gap.
Is the symmetry of the waveform? It's an S wave?
Yes.
It's a singlet S wave.
Yes.
Even if you have the bands or two bands.
Yes.
Sorry. Yeah. So the question was if it was S wave, and the answer was yes.
Yes. So actually, so for smaller Ks, smaller than K delta, which is determined by the order parameter, it is the same. The wave function is the same as the BCS wave function, but with equal coherences. So it's so for this narrow layer in momentum space of widths of 2 delta, you have paired electrons the same as in BCS, but with equal coherences. And if you go to the upper band for higher case, you have vacuum. And if you go into the lower band, also for higher case, you have Fermi C again. And delta is of course a consistent parameter. I can show you later. So in some sense, what you have here is a kind of Fermi C with an additional layer of ice on top of that. And as I will show you later, the analogy between frozen puddles on the street and frozen Fermi sea goes even further, because you cannot disturb the surface of water if it is slightly frozen, and it's not easy to disturb, right? The same is also here. You cannot easily perturb Fermi sea if it is covered by such kind of ice. All right, so this is the order parameter which I was talking about. This is a solution as a function of temperature. So it's the first sight. It looks very similar to the BCS, right? So you have critical temperature, you have a delta at a zero temperature, but the order parameter equation doesn't look the same as for BCS. So it's actually much simpler, in fact. So you don't have a prefactor depending on the delta and the electron energy. Instead of you have just occupation in terms of Fermi-Dirac. And most important here is that you have no solution for parabolic bands at all. So you must have some kind of flatness to have a solution in the first place. That's the reason why I in the title you have seen that it's flat band specific state. It doesn't exist in a conventional parabolic bands. That's probably the reason why people didn't notice it before, because yeah, so you need a really specific bands to see that it does exist. Yes.
So correct me if I'm wrong. You're in 2 dimensions, right?
Yes, in 2 dimensions. But in principle, you can work in one
but for this calculation in 2 dimensions, if p is equal to 4,
yes,
the charge susceptibility will diverge.
Charge susceptibility
Will diverge when you go to the band, because it's a very flat band. If the charge susceptibility diverges, then you have tons of other instabilities, like phase separation, so it's not, if you just, if you do a real calculation, or if you take fluctuations, it's not obvious that this state will even survive for the p equal 4 and that nothing else will come in.
Absolutely. Therefore, I had this first slide, second slide about mean field disadvantages. So mean field doesn't guarantee you that this is indeed, this solution of the true many-body Hamiltonian. It just gives you a possibility, not necessity. It may exist, but it may not exist, because it's just this very small fraction of the big many-body Hamiltonian which I'm considering. You're absolutely right. So that's no guarantee. All right. So the most remarkable property of this order parameter equation state is that if you go with p much larger than 2, then interaction strength doesn't really matter. So you just have a very nice relation between order parameter at t equals 0 and the critical temperature itself, and just double critical temperature in energy units, of course. And that's related to the extreme divergence of the density of states. If you have very high density of states, it doesn't really matter how strong your interaction. It's just enough to have very tiny, infinitely small interaction. Then you already transition into the correlated state, if p is very large. Okay. Of course, we have to check whether this ground state really exists, at least within mean field theory. So, of course, if you want to have a real good answer, we have to do QMC or something like that. But so at least we have to check that our ground state is below the normal state. Otherwise, we have no chance at all. And indeed, so if p is larger than 2, then the energy difference between our ground state and the normal state is negative. So that means our state is below normal state. But so to have a really like a big difference, you have to assume that the p is much larger than 2. Otherwise, if the interaction strength is small, then even if p like 4, you still have like a small number in the power of 3 or 4, something like that, right? So it's still, the difference is very small. So therefore, you have to assume that it's really flat to have a significant difference between normal state and ground state energy. So it's again related to the high density of states. You have to have high density of states to have such kind of state. All right. Okay, now we can talk about quasi-particle excitations. So of course you can consider our state in terms of electrons, electron occupation I have shown you before, but you can also think in terms of quasi-particles. So you have two types of quasi-particles. One is type 0, like we denote here gamma naught, but there are also like another quasi-particles of the same type, which have a zero gap energy. Okay, infinitesimally small energy to excite. And we have a types of quasi-particle type 1, which need finite energy to excite, at least delta. You have to invest at least delta of energy to excite such quasi-particles. And our electrons is in fact superpositions of these two quasi-particles. So therefore, they are made of zero gap excitations and finite gap excitations. So therefore, to perturb our electrons, we may need we cannot do it elastically, most likely, and we can check it explicitly considering such kind of Hamiltonian like shown here, which takes into account all scattering channels. So kappa is a band index, k is usually momentum, and but what we have to restrict here is a spin flip. So if the scatterers are magnetic, then we have to consider spin flip, so that's spin up to spin down and back, and then it doesn't work. But as long as scatterers are non-magnetic, then we can make a Bogoliubov transformation here, and then we arrive at the long line of many quasi-particle creation operators. But all terms here again made of quasi-particle excitation of type 1 and quasi-particle excitation of type 0. So therefore, when you calculate all possible scattering channels, like expectation values of each term, so it will necessarily vanish for elastic scattering for 0. So when energy doesn't change, and as a consequence, so if you solve everything correctly, so Boltzmann equation for quasi-particles, your relaxation time, momentum relaxation time, will be infinite. That means your conductivity should be infinite unless you have some magnetic scatterers or phonons or something like which can change your energy. Okay, so we have like 6 minutes, right? Of course, the first question you may ask whether such state can exist in reality. I cannot give you answer within true many-body solution, not mean field, because I don't know how to do that yet. But at least there are some indications, experimental indications that similar manifestation which we predict can exist. So one of them is twisted multilayer graphene. So you definitely know that twisted graphene structures at some medical angle, they have extremely flat bands. And some of twisted multilayer graphene at some doping levels, they indeed indicate sudden resistivity drop at about 5K. So which we believe that it is critical temperature we are looking for. And you have very sharp resistivity drop, like exactly what we expect. But of course, it may be something else, right? So it doesn't guarantee you that it's exactly the state. But at least this is what you can think about. Another example is sodium cobalt oxide. So I have discovered this paper recently. So what they measure is conductivity versus temperature and magnetic field, and it did again. So you see resistivity suddenly changes, conductivity in this case suddenly increases by orders of magnitude again at the critical temperature of 5K. Even though these two materials are completely different, the only similarity is here that both have flat bands, and the transport is two-dimensional there. So this is only two common properties of these materials, but everything else is completely different. Which one is magnetic, which one is not, for example. And then you also have a critical magnetic field which can kill this correlated state. So then we can do something similar what usually BCS people do. So we can balance density of magnetic field and the difference between energy difference in normal and our correlated state, and we'll balance them and find a critical magnetic field, which will be given by this equation. So here Tc is our critical temperature, omega is the volume of the brilliant zone, and mu is the magnetic permittivity. And then indeed, so if we assume that permittivity is like typical for cobalt oxide with about 100, then indeed this relation holds as measured. So indeed, if you put here 5K and on the left you have 20 Tesla, indeed the equation is correct. But of course, it again doesn't guarantee you that it's exactly the state we are looking for, but it looks like maybe it's just coincidence. Okay, so all right, so I'm already close to the end. So this is a conclusion. So the main take-home message is the following. So if we have band touching between flat bands and have a very high density of states at its touching point, and assume cross-band pairing, so we need two components: high density of states, I would say like extremely high density of states, and cross-band pairing. Then the manifestation will be that resistivity will drop at certain critical temperature, and we have a kind of novel state, which we call Fermi ice or frozen Fermi liquid, which can explain such a behavior, at least phenomenologically. So now, at the final slide, I will show you outlook, which I think can somehow reproduce what we have in our mean field theory on lattice. We have to consider Lib lattice, I guess, because it gives us exactly what we want. So it has band touching. So the conduction and valence band are touching in a single point. But of course, if we just leave them, the two of them, the density of state will be negligible at the band touching point. So therefore, but in the Lib lattice, we have a third band, which is completely flat. And if we assume that all sides and nearest neighbor links are equivalent, then this flat band intercepts exactly the band touching point. And this is exactly what we want. So we have two bands, and then the third band provides us very high density of states. But still, the second component is still not clear how we can get it. So how we can make how we can make electrons pair across, not at the same energy. Yeah. So okay, that's all for now. Yeah. Thank you.
Thank you for a nice talk. Are there any questions, either from the audience or from Zoom?
Thanks for the talk. I'm pretty sure you said it, but I may have missed it. What was the form of the interaction that you were assuming in the mean field treatment? Was this like attractive Hubbard interaction or something else?
Well, so it is attractive, it's for sure. It will not work for repulsive. And I have assumed that the Fourier component of the interaction potential is just a constant, which is very typical for BCS-like theories.
Like you would get for a Hubbard interaction if you look in momentum space.
Yes,
the Fourier component would also be Q independent.
That's true, but usually if you talk about Hubbard, you assume some lattice.
Yeah.
And I didn't assume a lattice in the first place, right? So that's not exactly Hubbard. Maybe you can get something like that if you assume Hubbard on this lattice, and then hopefully you can get something similar.
Yeah. Now, if I try to connect to the Hubbard model, if I take a Hubbard model, and I understand that this is a lattice and you were looking at the continuum, but if I take the Hubbard model itself on a square lattice and I make the band flat, I have to reduce the hopping amplitude T, and then the critical temperature will vanish like T square over U. So if I go, but here you say when you go to flatter and flatter bands, by increasing the power P, somehow you get to a gap equation that barely depends on you. So how can I make sense of this?
Okay, first comment. So I think you cannot make a bands flat, at least in my sense, just by changing hopping, because so it will, the dispersion will be still the same. So you effectively change effective mass if you change T. So therefore,
that's heavier until I get to the limit.
They're still parabolic, right? So and they're not flat in the sense that you have divergence of the density of states, right?
Well, if I have no hopping, all the states are at zero energy, and I would have a divergent density of states at zero energy. I mean, as much as I can have a divergent state density of states on a finite lattice. So it's always about
from this point of view. From this point of view, it's probably correct. But anyway, so and the second part of the question is sorry, I have missed.
How to make sense of a
so why you have a independent sorry, why you have delta independent of interactions if you have very flat bands? That's exactly the point. So you have to have density of states 1 over energy.
Yes.
To have this because it's at zero energy, then the density of states will be infinite.
Yeah.
So and if your density of states of infinite, then your very small interaction will already make your system transition into the correlated state. This is the point. Of course, you still define interactions, but you can make it with very tiny interactions if your density of states is divergent.
Maybe we should talk after the seminar at some point.
Any more questions?
So you showed that you compared with the normal state and you get lower energy, but you also compare with the normal superconducting state?
Oh. Yeah, it's good question. So of course I did. And if you have flat bands, then these two states are competing. So if it is parabolic, then the ground state of it's not okay. In a parabolic case, it doesn't exist at all. But if it is flat but not very flat, then it is nearly degenerate with a normal state. And if you make it very flat, then it is nearly degenerate with a BCS state.
You must have tried with Maxim. Did you guys try some models? Can you engineer models to get arbitrary P's?
Yeah, we have tried with Maxim some time ago.
Yeah, I know you multilayer graphene.
So you can use multilayer graphene, but you need.
I'm sorry.
So you can look at multilayer graphene, but you need ABC stacking. So you always have to shift it by 1 unit cell, which is thermodynamically not a stable configuration, but it can be built in the lab.
Yeah.
And there you can have quadratic, cubic, quartic dispersions. And in an experiment, they actually do see superconductivity, but you have a few complications coming compared to here. On one hand, you're looking at the low energy physics around the Dirac points, so you will at least have 2 Valley degrees of freedom. And I think you also get sublattice. So you have multiple flavors of the band systems that you have. So there are competing instabilities. And I think they only see superconductivity when they have a perpendicular displacement field where you actually gap out the band touching. And it's triplets. It's most likely triplet superconductivity due to Pauli violation.
Yeah, so that's a good comment. And so the reason I didn't tell about ABC stack graphene is because nobody saw sudden resistivity drop there experimentally. Nobody saw. Nobody observed sudden resistivity drop, but not superconducting one. No, because what we have here is a resistivity drop, which looks similar like a superconducting drop, but it is not superconducting. And what you usually see in a graphene is either just normal behavior, or superconducting drop with displacement field. Yes, but nothing like that. So phenomenologically, we have nothing to consider.
So there's no stiffness. The stiffness is zero. The superfluid density is zero. I mean, if you calculate the stiffness, you will get zero.
I did calculate, probably yes.
That's because if the resistivity doesn't drop to zero, then it has to.
So why would this be the case? Because if you have, if you go to the p equals infinity limit or start thinking about it from that perspective, then you essentially have a flat band. So this is like having multi-orbit or multi-band superconductivity. So when I write down a pairing wave function, all I need, since it's two fermions, it has to be overall antisymmetric. Fine, I can make it a spin singlet to have the antisymmetry of the wave function, and then I need a symmetric combination of the band indices. So why would this, and if this pairs, it's essentially a pairing at the Fermi energy or at the chemical potential, why would this not be a superconductor without superfluid stiffness?
Well, so that's because initially pairing was assumed not BCS pairing. So this is a technical answer.
But the difference between not BCS pairing is that you pair between different bands, right?
No. So you have to distinguish between interband pairing and crossband pairing.
Yes.
Because interband pairing is still BCS like pairing, but just in also you pair time reversal states which have the same energy. And here, it is crossband pairing. You have to pair across the band touching point. So
Johan is correct. It's still correct. I mean, if you go to P infinity, there's no notion of a cross. Energetically, it's the same, right? So I think his point is correct. I mean, well, at least worth thinking about.
But you cannot change symmetry in such a simple way, right? So
you can change. Your answer was energetics. So you can change energetics.
So even at a very high P, you still have your Vignale transformation still has this symmetric type, so with equal coherences. It doesn't really matter which whether UP is like 1,000 or 1 billion, right? So your Vignale transformation is still symmetric, and this symmetry makes a difference.
So if you calculate the superfluid density, it will be zero. That's your claim.
Yes,
that can be calculated.
So, yeah.
Right.
Any more questions? Online, maybe? Yeah.
Hi. Maybe I have some little questions. I just still want to know whether it's stable or not, and the symmetry. Which symmetry have you only have the time reversal symmetry or other symmetry? Because I know that at least for the P equal to 2, it's a quantitative band touching. If we have the time reversal and C4 or C6, it will be topological stable. But for another P, I just want to know whether it's that theory to or what's the symmetry you need to protect that it is stable.
So okay, it's a good question about symmetries. Okay, so just to I would like to first repeat. So we don't break time reversal symmetries for sure. So what we have to maintain is a symmetry between upper and lower bands. So they must have the same dispersion, and we must have Fermi energy crossing the band touching point. So if we break this symmetry, so if we don't maintain conduction valence band symmetry, then it doesn't work. So dispersion must be the same in both bands. Fermi energy must be at the band touching point. So that's the answer. So this symmetries must be maintained. Yeah.
Okay, no more questions. Maybe you can move on because then we still have another presentation. Another round of applause.